We have talked about rigid bodies in the general case, how they come about as an extension of the point particle model, what they are, and how to identify them. Now let's consider the particular case of rigid body motion, which is rotational. That is, rigid body rotational motion. So the first thing to do to consider rigid body rotation is to define a rotation axis, the line about which the rigid body is rotating. The rotation axis will point in the direction of angular velocity. So for an example, consider this rigid body rotating about the axis of rotation that I have denoted in red. You need to imagine this as a line that's coming out of the page and going into the page. It's the line about which this rigid body is rotating. I've denoted the direction of the rotation with this angular velocity omega, and it is a counterclockwise rotation. This angular velocity, therefore, is pointing out of the page. And so we see the axis of rotation is going out of the page. And of course, since the axis of rotation is a line, also going into the page. They are on the same line. Notice that I have made mention of a rotation axis as though there is only one. You might question, especially in the discrete case for rigid bodies, whether the particles on the rigid body or composing the rigid body, whether they might have different angular velocities. And the answer is, because the particles are all moving as one object, then the angular velocities must be the same for each particle on the object, or for each particle composing the object. And all the particles will therefore rotate about the same rotation axis. It has to be that way because otherwise the distances between the particles will change, and then it would no longer be a rigid body. That is the case of rotational motion, but it also applies to translational motion also. Because all the particles are moving as one object, each particle of the rigid body must also have the same translational velocity, else the distances between the particles would change. For example, consider these two point masses dm on this rigid body. If they are moving in different directions translationally, they are moving apart from each other. And that line will change. This rigid body is going to change its shape. Similarly, if they are rotating about different rotation axes or with different omegas, then as they move about these circles, the length of that blue line will change. The distance between them will change, and the rigid body will be changing its shape and deforming as the object rotates. As an aside, although we will not deal with this case, if you have a system of discrete particles like this, and they are not a rigid body, then to deal with the general case of their motion, you'll just need to give each particle their own axis of rotation about which they are rotating. And so you would have something like this, which is pretty wild. But now finally, let's think about examples in the real world of rigid bodies that rotate. It's pretty easy to think of them. Just think of an example of a rigid body and then start making it rotate. And there you go. You have a rigid body rotating. But to give you some specific examples, we have pulleys, for example. They are spinning disks. Other spinning disks are also examples of rigid bodies undergoing rotational motion, rigid body rotation, like a CD player or an old record player, anything. You could also get a bit creative with understanding rotational motion of rigid bodies. Whenever you open a door, it is rotating about its hinges, however briefly. Or you might have an actual revolving door that rotates around as you move in a 360-degree way. Or maybe it's even automatically rotating in a 360-degree way, powered by a motor. Ceiling fans, when they spin, that's another example of rigid body rotation. Windmills with their wind turbines, those are spinning about in rigid body rotation. Anything that is a rigid body that can be modeled as a rigid body and is rotating, that is an example of rigid body rotation.